Bismillahirrahmanirrahim. Greetings. The rigorous mathematical definition of limit, known as the delta epsilon definition of limit or epsilon delta definition of limit, is a bit abstract and difficult for most of the students taking calculus for the first time. Now, in this lecture and a few more to follow, I intend to dig to the root of the concept and come up with an intuitive definition, intuitive feeling and definition of limit, and once that is achieved, hopefully will take or melt away the abstract part of the definition. After that, I intend to go over the related theorems and the proof of them, and the last step will be to solve related problem. So again, I repeat myself, that may take a few lectures to complete that one. So let's get started, shall we? Now I start with the definition that I mentioned is the rigorous mathematical definition or analytical definition of the limit, and read it for you and go over them. But I'm not going to go too deep into that. As I mentioned, I'm going to go through examples and try to melt away the abstract part of it. Now, he says that limit of f of x, of course we are talking that f of x is defined for all the values of x except c. So limit of f of x as x approaches c equals to L if and only if given epsilon positive, epsilon is a number, it ends up to be later on if we talk about that, is arbitrary. Given epsilon greater than 0, one can find a delta greater than 0 such that for all x different than c, that is a notation that means exactly the same thing. When you say greater than 0, that means x cannot be equal to c. If that was not given greater than 0, then the possibility of x equal to c will be there. So that is the notation for that. Then for if x minus c absolute value less than delta greater than 0, then f of x minus L is less than epsilon. All right? Now, this that I wrote here is a shorthand mathematical symbol representing the exactly same this definition. Now, this shorthand representation of the definition of limit in the textbook is almost one line, is a little bit less than one line. And that is fascinating because this shorthand will, about 5 or 6 pages you have to write and talk about the concept of the limit, and is abbreviated and put in kind of short in a symbolic form in less than one line, and that is fantastic for communication, and also is very effective in better comprehension of the subject. Okay, we come back to that. Now, before I proceed further, please do not let this abstract definition I just read for you to discourage you. If you are watching this for the first time and you are going to take calculus, don't let that to discourage you and run away. When we finish from all these few lectures, then you will end up to be, this definition comes fascinating, very appealing to you, and you will love it, and especially the shorthand mathematical symbol form of that. Okay, then, now let's start the main part of the lecture, if we may. Sorry for the primitive equipment I have, and hopefully, inshallah, someday soon, I will have access to a classroom. Okay, now, let me start with this, if I may. Now, suppose we want to add these numbers, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 and so on and so forth. For what? For the there is no end to the infinity. As again one, and this is a typical representation of each term, 1/2 to the n. And this is a symbolic mathematical shorthand of this 1 plus half plus 1/4 and so on and so forth. You are hopefully familiar with this kind of representation of sum of big numbers. Now, what is the sum of this? Now, if you haven't seen this one before, if the first time you are being exposed, you say, I don't know, it's impossible. I cannot see it and add and add and add and add 1, then 1/2, then 1/4, then 1/8, then 1/16, and so on and so forth. It will go forever. The whole universe will go out of existence and still I haven't finished. I keep going. So I don't know, it just intuitively at the first glance, it looks like doesn't make sense. I cannot add them. So what we do, we go through some kind of, in a sense, fairy tale story of practical situation so that we can get the, intuitively we can say that this may have an end. Then we can proceed from that. So this is what I come with. Now suppose a frog can jump with the rate of 1, let's say, yard per second. The unit is immaterial, all right? So he jumps with the manner that he jumps is that after the first jump, which takes 1 yard, the other jumps that he makes, each of the jump will be half of the previous one. So the first jump will be 1 yard, the second jump will be half of the one, which is 1/2, the third one will be half of the previous one, which will be half of the half, which is 1/4. The next one will be the half of the previous one, which is half of the 1/4, which is 1/8, and so on and so forth. That is the way the frog is jumping, in a straight line, let's say. Now, intuitively, we know that eventually there is an end. The frog is not going to go around the earth. It's 1/2, then 1 and 1/2, then 1/4, and finally will hit the dead end, will hit the wall or something, will not go further than that point. There is a point that may never reach, but will never go further than that. Intuitively, we know that it will be the case. So based on this observation, let's see if we can add them mathematically. The 1 plus 1/2 plus 1/4 and so on and so forth. Let's see if we can do that. Not algebraically or mathematically. Now, how do we find the distance? We want to know how far the frog has jumped, how far the distance that the frog has covered. Distance equals to rate times time. We know that formula from driving car. We have been exposed to this distance equal rate times time for all of our life. Now, distance equal rate times time. We know the rate of the jumping of the frog, but we don't know the time. So we cannot find the distance. You follow me? Distance equal rate times time. We know the rate of that is 1 yard per second as our assumption was, but we don't know the time. So we cannot find the distance that the frog has covered for jumping half and half and half and half of the previous one and so on and so forth. So, but when something like that happens in mathematics, they always, mathematicians seek for other ways to hopefully find a solution for that problem. And that's exactly what we are going to do. So what we do is we are going to go through mathematics. Now, knowing in advance that the frog will definitely not pass certain point, will get closer and closer to that point, but will never pass that one from our intuitively from the jump of the frog, we came to that conclusion. Therefore, let's say the distance that the frog can ever reach, cover, let that to be S. Let S to be that. So right now, we have S equals 1 plus 1 half plus 1 fourth plus 1 eighth and so on and so forth. And let's see if we can solve this one now, algebraically. So what I did here, as you notice, you can take a note, I think it's large enough. Now I factor 1 half out of all these terms. Simple factoring, huh? And I end up with these 2 plus 1 half plus 1 fourth and so on. Because when I factor 1 half, when I multiply 1 half by 2, I get 1. Is that right? And when I multiply 1 half by 1, I get half. So if I multiply this, I distribute half to this, I get this one. So I haven't done anything wrong. It's just algebraic manipulation, algebraic abracadabra. So now, when I do that, look what happens. I have 2 plus 1 plus 1 half plus 1 fourth plus 1 eighth. But this 1 plus 1 half plus 1 fourth plus 1 eighth is exactly what my S was to begin with. Is that right? Look at it. So my equation end up to be S equals to 1 half of parenthesis 2 plus S. Is that right? Now, to solve this one is grade school. So what do? I just arrange it. I distribute 1 half to that. 1 half times 2 is 1. 1 half times S is 1 half S. Then you can add to both sides negative 1 half of S, or bring 1 half of X to the other side. You get half of S equals to 1, and then multiply both sides by 2, you get S equals to 2. Fantastic. Isn't that? So we end up to know how far the frog will cover, that will never reach, but eventually, forever, if he jumps, he will cover not more than 2 yards. That is the limit can ever reach. And theoretically, we'll never reach that one, huh? We come to that again. Okay, so far, so good, huh? Now, let me do the same problem in another way, just for the sake of it. That is the beauty of also algebra. Abracadabra. Huh? Now, before I factor 2 odd, I factor 1 half odd from the whole entire series. Here, I multiply this series. I multiply by 2. All right. Look what happens when I multiply by 2. The 1 becomes 2. The 1 half becomes 1. And so on and so forth. You see that? Again, the same S comes back again. You see that? Because 1 plus 1 half plus 1 fourth plus 1 eighth is the same S. So I end up with 2S, because I multiply both sides by 2. 2S equal to what? Equal to 2 plus S. So add to both sides negative S, you get S equals to 2. Isn't that fantastic? So that is another way to look at it, if you like this one better than previous one that I factored 1 half of it. Again, so far so good. By the way, one other thing that we mentioned before I forget is that because addition is a binary operation, is that right? You have to take 2 at the time. So you add 1 and 1 and 1 half, which is 3 half. And when you get that result, you add that one to 1 fourth, and so on and so forth. And by doing that, you get 1, the next one will be 3 and a half, next one will be 3 and a half plus 1 fourth, next one will be 3 and a half plus 1 fourth plus 1 eighth, and so on and so forth. If you put comma between them, then this series become what? Become a sequence. That sequence is called a sequence of partial sum. Now, later on you will see it in calculus 2, that if sequence of partial sum converges, which means has a limit, then this corresponding series will also have a limit, converges as answer. It's just a little bit aside. Okay, now let me go to next, if I may. Now, let's assume that we don't know, we don't go through the frog. Somebody gave us this one and it said add them. So again, I go over that one more time. Intuitively, you say, hey, I am supposed to add 1 plus 1/2 plus 1/4 and so on forever. That means I cannot go forever. It doesn't make sense. So that means first glance and intuitively, this should not have any answer. Now, we assume, suppose that this does have answer. So let S or X or something to be representing this answer. Then the question you will ask that, not so fast. Why? What about if your assumption is false? You said suppose this addition, this summation has a finite answer. What about if your assumption is false? And that is a good question to ask, but when you deal with the if-then statement, conditional statement, you don't question the if part of it. You don't question the premises given in the if part of the statement. You don't question that. Based on that if part, based on premises given, you proceed. You don't question it, remember that. So when I say suppose, or I assume that there is such a S, you don't ask question that, wait, not so fast, how do you know that your assumption is correct? Based on assumption, I am proceeding. Do you follow me? Now, if the assumption ends up to be false, that does happen, in the if-this statement, that is the inverse. If P, then Q, the inverse of that is if not P, then not Q. But that is a statement in its own right. So that is another statement. So here, if my assumption ends up to be wrong, then I come back with some very absurd answer. Like I end up with 2 equals to 5, or -1 equals to 3, or something like that. So I come up with contradiction. So I immediately notice that my assumption was false. So don't feel kind of question, which is a very good question to ask. Hey, what about if your assumption is false? But again, I repeat myself, if that happens, you end up in the end with kind of contradiction. So have the courage to start that. So suppose that this does have answer, as a finite answer. Then let S represent that answer. Let S to be equal to 1 plus 1/2 plus 1/4 plus 1/8 and so on and so forth. Then you go and proceed as we have already done it, and you end up to be S was equal to 2. Isn't that interesting? That's the beauty of mathematics. So my assumption was not was valid, was not false. Okay, so that is another thing if we didn't go through the practical example of the frog. Now the question is not another question for the curious student or the mathematician are always curious about that. Now I know that distance equals rate times time. So can I somehow solve this problem using that formula? I couldn't use it because I didn't have the time. So the answer is yes, we can do that. So we are going to go through another fairy tale story, that with that story we are going to bring the time as a catalyst. You will see that, what I mean for that. So the story that I'm about to tell you is equivalent to the jump of the frog, but in a different way. That's what equivalent means, in a different way, but as a catalyst is going to help me to bring the time into the picture and solve it with respect to distance equal to rate times time. Very fascinating, huh? So that's what I wrote for you. And as a matter of fact, what I'm going to come up with is called Zeno's paradox. Zeno's paradox. There are 9 of them altogether. Zeno was a philosopher over 2,500 years ago, and he came up with some very, and paradox means something that theoretical, is something that logically makes sense, 100%, but that is not true in application. We cannot use it in application in the way that we live in this planet Earth. Maybe in some other planet, gobbledygook, that could be applied, but not in the planet Earth. That's what we call it paradox. So let's go to the Zeno's paradox that will come and solve we can bring the time in our picture, so that we can use the distance equal rate times time to solve the 1 plus 1/2 and so on, the distance that the frog was jumping altogether. Now suppose that now we put the story, we change the story, it's a fairy tale story, how we change the story into a race between not rabbit, let's say hare, because hare is rabbit, but it's a little bit larger than rabbit and can run faster than rabbit. It's a little bit different, but it's in the family of rabbit. Let's say the race of a rabbit and tortoise. Tortoise is a turtle, but lives on the land. So if you put the tortoise into the water, it will drown. But turtle can swim in the water. So that's a difference. So let's now we are going to have the race between what? Between a hare and what? And a tortoise. Now the race will start with the tortoise being 1 yard head start. So tortoise is 1 yard ahead of him, and the hare is 1 yard behind, and then the time starts. The stop time. Okay, the time starts and the race starts. Now, when the hare, after 1 second, where is he now after 1 second? His rate of running is 1 yard per second. And let's say I forgot to mention also the rate of the turtle walking is a 1/2 yard per second. Again, it's a fairy tale story. I made up those numbers. Now, in that case, when 1 second later or 1 minute later, again the unit is immaterial. Let's say 1 second later, the hare is where the turtle was 1 second before. Is that right? Now, in that time duration, as the time expires, during that time, the turtle has moved 1/2 yard ahead, because in 1 second, the turtle will go 1/2 yard, because that is his rate of walking or running, 1/2 yard per second. So in 1 second, he's 1/2 yard ahead. So now the situation is that the hare is where the turtle was a second before. Now the hare should catch the turtles. Now, how far his rate of change? His rate of running is remember is 1 yard per second. So he has to go now 1/2 second, so that he be same place that the tortoise was, because the aim is to catch the tortoise. So by that 1/2 second, also the time is passing same for both of them. So is the time the tortoise will be 1/2 second, which is what, which is 1/4 of a yard is ahead. Is now in new location. You follow what's going on? It's very interesting. And then the hare now should, in order to catch the tortoise, should be being same place that the tortoise was 1/4 of a second before. So when he reached that, during that interval of time, because of the rate of the tortoise is 1/2 yard per second, is 1/4, which is 1/8, is ahead again. And this process can continue but forever, theoretically. So in reality, the hare will never be able to catch the tortoise. That is what we call it paradox. But in application, we know it will catch it, and we already know what the answer is, how far it goes to catch it. So this is called, again, I repeat myself, it's called a paradox. And for 2,500 years, it was mind-boggling for all the mathematicians and physicists and philosophers were very interesting for this kind of paradoxes. Now, again, this kind of paradox is a theoretical logically is acceptable, but in practice is not. All right? Now, let me see what I have. Now, I have written this, what I just talked about. I have written for those of you who may want to take a notes. And so I don't go over them. I just put it here, and you can always pause your computer, write it if you wish, and then I will proceed. Okay, then the next one is, no, don't forget the goal is we brought the turtle, or the tortoise, excuse me, we brought the tortoise into the picture as a catalyst to solve the problem that we had, the problem of the jumping frog, to see how far they cover. To use it, distance equal to rate times time formula. So again, I repeat myself for the third and fourth time, the tortoise and the time is the catalyst to the same problem as the jump of the frog. Okay, here, let x to be the distance that the hare will cover that eventually, theoretically, will never reach, I'm repeating myself, will never be able to catch the tortoise. But let's see, that is the place that eventually, if it ever reach it, it will catch the tortoise on that. And in practice, in reality, in real world that we live, definitely we know that the hare will catch the tortoise. So let x to be that distance, the distance that will catch it, the tortoise. Now, then you may be tempted to set the equation, okay, if x is the distance that the hare will cover to catch the tortoise, so the distance the tortoise will cover will be x negative 1, x minus 1, because he had one yard head start. Okay, then you may be tempted to set up x equal to x minus 1. But x equal to x minus 1 is nonsense, isn't it? There is no such an equation in mathematics. No number could be equal to itself minus 1, not even 0. So you know immediately you set up your equation wrong. So you say, okay, what else can I do? The second was because you need to make equation, huh? So we couldn't make the equation setting up with respect to the distance that they cover. So next one is to set up our equation with respect to the rate. But they have different rate. The rate that the hare runs is what? 1 yard per second. The rate that the tortoise was running was half a yard per second. So we cannot set them equal. Then we say, okay, what else we can? The person who started the time for the race, the time is passing same for both of them. Isn't that right? The time is passing same for both, the hare and the tortoise. So we take advantage of that and we set our equation based on the time. So what is the time that the hare will cover? Time is what? Distance divided by rate, which is x divided by 1 yard per second. So if you drop the unit, it's x over 1. And what is the time that the tortoise will go? Distance divided by rate. The distance that the tortoise cover is x minus 1, and the rate of that is half a yard per second. So if you drop the unit, it will be x minus 1 over what? Over half. Bingo. Lo and behold, we got the answer. So we have what? We have, I haven't written that one, possibly next one. So we have x over 1 equal to x minus 1 over 1 half. And that is the grade school equation to solve. So let me put that one up for you. And you know that distance equal rate times time. The time that for the hare, I wrote that is distance divided by rate. And the time that passes for the tortoise is x minus 1 over its rate. And here it is x over 1. And this one is x minus 1 over half. And the rest of them is very simple algebraic manipulation. And we end up with the answer of 2. Isn't that fascinating? So we did use the distance equal rate times time to find the distance that the frog achieve by bringing what? By bringing the tortoise and the time into the picture as a catalyst. It's very fascinating. Now looks like we have the answer for the Zeno's paradox. Hooray! Hooray! For 2,500 years, the mathematician, the philosophers, the physicists were working on Zeno's paradox, and they couldn't come. They make sense to them and doesn't make sense to them to begin with. So we came up that yes, we can make sense out of it, and it is the answer is 2 in this example. So that means, hey man, we have to get this guy. His name is Ali Umar. This guy should get 3 Nobel Prizes, 1 for physics, 1 for philosophy, and 1 for mathematics, because he just solved the Zeno's paradox. Fantastic. So please do not let anybody knows about my solution, so that they don't go and publish it ahead of me and they get the Nobel Prize. So they will be stealing it from me. Okay, then the next video that I will cover, as I already mentioned in the introduction of this lecture, that I will be going digging into the root and coming up with the intuitive definition of limit, and try to kind of melt away the abstract part of the definition. So then the definition will become very kind of sweet and appealing, and you love it, and hopefully, inshallah, that will be the case. Okay, then I thank you for watching, and please don't forget to watch the rest of the videos that I'm going to upload. And also I'm intending to upload one a long lecture about absolute value of x equal to x if x is greater than or equal 0, is minus x if x is negative. That is just a joke. The students memorize, they don't know what it is, but just I will put at least 1 hour just for the subject of absolute value. So there is more into that. And the reason I brought that subject up, because the definition of the delta epsilon definition of limit deals with absolute value. Okay, then I thank you for watching, and I wish you all prosperity and good health, and please stay safe. So long.